Okay, welcome everybody. Hopefully you can all hear and see me. For this lecture, we're going to do a review of correlation. Now, I know correlation is something that you learned in 221, but because we're going to be covering or learning for the first time about linear regression in this class, I think it's important that we do a review of correlation. So these are the lecture slides that I use for my 221 class. So they're a bit comprehensive. You'll forgive me, hopefully, if I speed through some parts. I'm going to just try to highlight the most important aspects of correlation for us to review in order to help us better understand or to more easily learn linear regression. Okay, so let's get started with this slideshow here. So in terms of the topics that are covered in the lecture, we'll talk about the scatter diagram or the scatter plot. Hopefully you have a lot of experience with those. We'll talk about the different patterns of correlation as a review. The correlation coefficient, how it's calculated by hand. We're not going to calculate it by hand in this class. I'm sure you had to do that in 221, but we'll definitely calculate it in SPSS for this class. How we interpret correlation coefficients, the problems that we run into with correlation and causality, and the coefficient of determination, which we'll see is essentially R squared, your correlation squared, and what that actually means. So starting off with the scatter diagram, the scatter diagram or scatter plot, as it's often called, is a graph that shows the location of each point formed by a pair of x and y scores. So the scatter plot is going to show a relationship, or hopefully reveal a relationship between two variables when, as the x score increases, the vertical height of the data points change, indicating that the scores are changing. Now that height can go up or down depending if the correlation is positive or negative. So we'll see that in a moment here. But when a relationship is present, the data points will form some type of diagonal shape that we'll be able to visualize essentially our data and visualize the directionality and strength of the relationship between the variables. So let's just take this data set here. It's very small, only 6 scores, right? 6 pairs of scores. So say we have the following data from a class of students, and we want to see if there's a relationship between the number of hours that a student studies and how well they perform on an exam. So let's just say we have these 6 students. We find out how many hours that they studied for the exam, and then we have their grade for their exam. So we can plot these on an x and y axes, right? So we can take our scores here. Let's just take our first pair of scores, that 2 and a 70. You see we can plot that there. Pretty easy. I know I'm cutting off some of the slide down here, but the x-axis is the hours that students studied, and that goes up to 7, and our y-axis is going to be the exam grade. Okay, so we know this person here studied for 2 hours on the x-axis, and they scored 70. So we'll go over to 2 and go up to 70, and this data point represents that person. So we're going to do this for all 6 of our pairs, all 6 of our students there. And we end up with the scatter plot that looks like this. So just by judging this, hopefully you can recall that this already looks like it's a pretty strong positive relationship going on, except for that last score, right? That score in red, that seems to not really fit in with the rest of the pair of scores. In fact, we would call that score an outlier, because it's not fitting in with the rest of the score. It's not fitting in with the general pattern that we see going on in the scatter plot. So what we do with outliers is a debatable question here, because they can kind of throw off our models. Less so with correlation. It becomes more of an issue with regression. So it's something that we will revisit, but we're definitely going to keep that score in. We only have 6 scores here, so we shouldn't be even thinking about what to do with outliers yet. But we already have this scatter plot, so we got these dots scattered all about. But to help us visualize the nature of the relationship between the 2 variables, we could actually insert a line. It's going to be just a single line that is designed or is put in there in a particular place to best represent all of the data that we have. And we call this line the line of best fit. So I didn't use any model, any regression model, or any formula to calculate that line. For this example, I just eyeballed it and said, yeah, that line looks like the line of best fit. Probably not, though. It's probably really not taking into account this outlier there. But hopefully you're just getting the groundwork that I'm trying to lay here. When we insert this line through our scatter plot, it's a single line, and we don't get to use multiple lines, and it's a straight line. It doesn't get to curve or anything. So you get one single straight line that best represents all of your data points. So it's kind of like the average, the line of your average data in a sense, right? So at least that's one way that we could think of it. If you only had one line to represent all of your data, what position would it be in? Where, how high, how low on that y-axis would it be, and what would its slope be? How much would it curve, and in which direction? Those are all types of questions that you can think about, because they will actually be important once we get to linear regression. It's kind of what linear regression is all about, is this line of best fit and using it to make predictions. But I don't want to jump ahead too much. So let's take a look at the different patterns of correlations. So a perfect correlation, or perfect positive correlation, we see in this example here, this first diagram, that as we increase 1 unit of measurement on X, whatever that might be, number of hours studied, whatever this interval might be, as we increase 1 unit on X, we are increasing exactly 1 unit on Y, and that pattern stays the same. So for 1 increase on the variable X, whatever that unit of measurement might be, we're increasing exactly 1 unit on Y as well. So we have perfect positive correlation there. The next example represents a perfect negative correlation. So in this case, as we're increasing 1 unit on the x-axis, we're decreasing by exactly 1 unit on the y-axis. whatever those measurements might be, they're proportional, right? So we increase 1 on x, we're going down on y. We increase another unit on x, we're going down another unit on y. And this creates a perfect negative correlation. This last diagram that I know I'm cutting off a bit, but hopefully you see here, there's no discernible pattern to these points on this dot, or on this scatter plot rather. These dots aren't really showing any type of pattern. This is a correlation of 0, and we see that the line of best fit is flat, meaning there's nothing happening there, right? So just to review what I said, here we have a perfect positive correlation between x and y. So as the variable x increases by 1 unit, variable y increases by 1 unit. So we get a perfect positive correlation. In this example, we saw that we have a perfect negative correlation between x and y. So as x is increasing y by 1 unit, y is decreasing by 1 unit. And in our last example, we don't see any patterns at all. So we have a 0 correlation, or correlation of 0. All 3 of these patterns are actually pretty rare to see in real data. Why? Because perfect correlations don't really exist. We already discussed issues that come with measurements, right? When we try to measure things, the error is just a fact of life. So even if 2 variables are perfectly correlated, chances are there would still be some statistical noise. There'll always be some margin of error in there. So it'd be pretty rare to find these types of perfect correlations. The same would go for a correlation of 0. Statistical noise might just produce maybe might as well be 0, something very close to 0, but might produce some type of coefficient in there, just by chance or just by coincidence, or by the way that we chose to measure things. So whenever you see perfect correlations like these, whether they be perfectly positive or perfect 0, like absolutely nothing, it's usually cause to kind of check to make sure you didn't do something wrong. You always kind of expect some error, some little variations in there. So the different patterns of correlations, not all relationships between 2 variables are going to take on this straight linear pattern. Luckily for you, we're only going to examine linear patterns in this class when it comes to correlation, and also when it comes to regression. But there are lots of different distribution shapes that these, let's say, or different shapes that these patterns between variables can take on. So when we use linear correlation to examine these types of patterns, it might be likely to show a correlation of 0. So sometimes when we end up with a correlation coefficient of 0, we might have to think, well, are we sure that this is a linear pattern? Maybe it's changing shape somewhere. Maybe it's actually not linear after all, and we're kind of missing out on the actual shape. So remember, when it comes to correlation, we're dealing with linear relationships or linear patterns between 2 variables. The same is going to hold true when we talk about regression in this class. So some common types of nonlinear relationships include quadratic trends, cubic trends, thought I had a third one there, but guess those are it. So quadratic trends and cubic trends. So let's take a look what a quadratic pattern might look like. So clearly this is not linear. We see that in quadratic patterns, the trend of the data point is changing directions. In this case, it changes direction once. So we can think of, two variables that might be associated with, two variables that might be related in this quadratic type of way. I'm just trying to think off the top of my head. Maybe age and stress, perhaps. So, as age increases, stress increases to a point, but then after a certain point in age, stress might start to decrease, as an example, right? So maybe when we're young kids, we have kind of low stress, starts getting up there till we get into the teen years, getting through college, kind of maybe peaks in midlife, where like the midlife crisis comes about, and hopefully we resolve that with some good therapy and maybe some antidepressants, and stress tends to go down maybe as we age. Let's hope so, right? Let's hope it doesn't get worse continually as we go on. So we can see here, if we just plopped in a line of best fit, and again I just drew that by hand in PowerPoint, so there's no formula associated with it, but the point is it's clearly not linear. But what if we only stopped our observation at this point on the x-axis? Then the distribution would, or the pattern of scores would look linear, right? Well, because we didn't view the rest of we stopped too early. So sometimes patterns that look like they're linear are actually not. It's just we didn't look at the full set of data. When it comes to cubic patterns, these are shapes that change direction twice, right? So in this case, we see the data taken on a positive kind of shape, right? As one's going up, the other's going up. Then looks like it's taken on a negative shape. So as x is increasing, now y is decreasing. And then we see an uptick again after some point on the y-axis as on the x-axis as scores are increasing. Y is increasing again. So we can think of some variables that might take on this shape as well. I think even just the pandemic is kind of taking on this shape, and as it's playing out is taking on this shape. You have an initial surge, say in many countries, where the number of cases are increasing as time is going on. Then they kind of level off, and the number of cases start to drop again. And then this is what the dreaded second wave is basically all about, right? This uptick in cases again. Unfortunately, when it comes to second waves of pandemics, where this one changes shape is usually a lot higher than the first wave. So, but that's the first thing that came to my mind as an example. Again, the whole point of this is to show that the line of best fit in this case is not linear. So, in examining linear patterns or using linear regression, which is what we'll be doing in this class, is not suitable for all all types of data, or to examine all types of relationships between variables. So relation or linear correlation and linear regression is not appropriate to examine those types of quadratic or cubic relationships. Instead, we use a analysis or a set of procedures called trend analysis, but we're not going to be discussing that in this class. That's something that I learned in grad school, so we're not going to be doing that here. Instead, we'll focus on linear correlation and linear regression. That'll be the next lecture. But when it comes to correlation, we will specifically learn how to compute and interpret or review how to compute and interpret Pearson's product moment correlation, which is used when we're examining relationships between two continuous variables. So variables that are essentially measured on interval and ratio scales. Okay, so how do we compute the Pearson product moment correlation coefficient? Let's just take this data that that we've been using, that we used earlier in our scatter plot example. This is the formula for, well, this is the conceptual formula for R, for the Pearson product moment correlation coefficient. So we see the z of x and z of y. It's what we call cross products. We'll see how that works out in a second, divided by the degrees of freedom. So it looks like a easy enough formula here if you have all the z-scores for x and all the z-scores for y. So what exactly is x and what is y? Well, when we were plotting it out on the scatter plot on the scatter diagram, we put x, or we put hours studied on the x-axis, and the grade on the y-axis, just because it makes more sense that way to visualize it. So when we take a look at this formula, the zx there, z of x, is the z-score for each person on the variable x, or hours studied. So we need to calculate some z-scores for hours studied for this column here. We need to turn these into z-scores. The z of y there is the z-score for each person on the variable y, or exam grade. So we're going to need to calculate the z-scores for these exam grades as well. Now, calculating z-scores can take quite a bit of time. We need to calculate the mean and the standard deviation, so there's a lot of work in there. I'm just going to go through it quickly just to remind you of all the work that goes into calculating Pearson's correlation coefficient, so you get a better understanding or appreciation for when SPSS does this for you in no time flat. So if we have the z of x and we have z of y, zx and zy is all the z-scores of x times the z-scores of y for each person. And in this formula, n is the number of pairs of scores, so not the number of individual scores, so the number of pairs. We have 6 pairs of scores. We could think of this also as n representing the number of participants, right? So n minus 1 would be our degrees of freedom, or 6 minus 1 it would be 5. Okay, so we first need to compute the z-scores for each person's raw score on the x and y variables. To do that, how do we compute a z-score. Well, hopefully you remember. If not, there it is. We take each individual x-score. Since we're going to start with the x variables, or the x variable scores. We take each individual x-score, we subtract out the mean, and we divide by the standard deviation. Well, we have each individual x-score there, so that's good, but we need to compute the mean and the standard deviation. Luckily for you, I already did that, right? Again, this is not a math lesson. I want you to understand what's actually going into computing these coefficients, so we have a better understanding of what they actually mean. So we got our mean and standard deviation there, and I even did it for our y raw scores as well, right? So that was kind of nice to everyone, 'cause, I did all the work there. But it's okay. SPS is going to take care of this stuff for us. So all we have to do is apply this formula. How do I get all these z-scores? Easy. I took 2 and I minused out the mean of 3.5 divided by the standard deviation of 1.87. And I got that z-score. I did that for all of my x-scores, and then for all of my y-scores, the exam grades, I did the same thing. I took 70 as my y's score, subtracted out the mean of my y-scores, 76.67, and divided by 12.91 to get a z-score of negative 0.52. Now, if you remember way back when you learned about the normal distribution, you know that the normal distribution is a z distribution, and the mean, median, and mode of the normal distribution is 0. So here's actual proof of that. So if you took the class with me, 221 with me, you know I hammered that in. But if you took it with someone else and you thought they were bullshitting you, there's actual proof. Go find the mean of these z-scores. It's gonna end up being 0. Then go find the standard deviation of these z-scores, and you're gonna find out that the standard deviation is gonna be 1. And it doesn't matter what set of z-scores you're using. All standardized scores will always have a mean of 0 and a standard deviation of 1. So if you remember, let me grab my little whiteboard here. If you remember, let me see, how do I do this? The normal distribution. Hopefully everyone can see my normal distribution. Something like that. Okay. We know that this value here is 0. That's the mean of the normal distribution. And each one of these are the standard deviations. It's going to come out really bad. Let me do it quickly and then I'll show you. Okay, so hopefully everyone can see that. It's basic normal distribution or z distribution. This is the mean. It's also the mean, median, and mode, right? And the standardized score is 0, and it's always going to be 0 no matter what data you have. The mean for any standardized distribution of standardized scores of z-scores will always be 0, and standard deviation will always be 1. That's why the normal distribution never changes. It always stays the same. The raw scores associated with these values change, right? So if you take a look at hours studied, when we standardize the mean is 3.5 right there. When we standardize it, it's 0, but the raw score equivalent would be 3.5, and each of these standard deviations would increase by 1.87 on the raw score scale. But once you standardize them, they're just 1. So, little bit off topic, but like I said, just to show you some proof as to how that normal distribution works. And if you don't believe me, go calculate those things yourself. Go calculate the mean and standard deviation for those z-scores, and you're going to find that the mean always will be 0, and they will always have a standard deviation of 1. Okay, so the next thing that we have to do is multiply the z-score of x and the z-scores of y for each person. So we have a new column over here, zx times zy. So I fill these in because we took the z-score of x for person 1, multiplied it by the z-score of y for person 1, and we end up with this cross product here. Okay, so all of these are cross products. These are just the result when we multiply the z-score of x and the z-score of y for each person. Now, when we add these up, these are called the sum of the cross products, right? So we sum these up. And in this case, we end up with 4.14. So we got the half of our equation is done now. All we have to do is divide this by the degrees of freedom. So we know that our degrees of freedom is n minus 1. In this case, we're talking about the number of pairs of scores. So n is 6, n minus 1 is 5. Easy enough. So we take the sum of our cross products, 4.14, divide by 5, and we end up with a correlation coefficient of 8.28. So hang on to that number there, 8.28. Okay, so we're gonna find out, what exactly that means, how to interpret it, and then I'm going to show you how we take care of that, or how we do this in SPSS without all this math. And this is not a whole lot of, well, it's a whole lot of math. It's just not difficult math. It's just redundant, time consuming, and there's a lot of room for error in here, right? It's just like if you messed up one of these calculations on the z-score, it could throw off your whole calculations, your whole statistical test. In this case could be crap, right? So, and these are only 6 pairs. Can you imagine if you had to do this with hundreds of pairs of scores all by hand? It's not fun, very tedious, and again, a lot of room for human error in there. So we just see here that I rounded this off. I'm cutting off this the score here, but we have a correlation of 8.28, or let me write this down, or 0.83, right? So sometimes when we are reporting correlations, it's customary just to round up that second digit after the decimal point. Okay, so we also have a computational formula for Pearson's correlation. The formula I showed you was more theoretical, kind of give you an idea of what is actually being done when we're computing correlation. Well, just to recap, we're taking all of our x-scores, transforming them into z-scores. We're taking all of our y-scores, transforming them into z-scores. Then we're multiplying all the z-scores for our x-scores, multiplying them by the z-scores of our y-scores, adding those up, and dividing by degrees of freedom. Again, lots of room for error in there. The computational formula is designed to make this process a lot easier when you're calculating correlation by hand. We don't need to memorize this for class. I'm not going to ask you to do this by hand in class, but let's just quickly go through this. Actually, you know what? Let's just pass over all of this. This is the computational formula. I wanted to show you the theoretical formula so you can see what is actually going on, but we're not going to be calculating this stuff by hand, and just for the sake of time, this is supposed to be a review. I'm just trying to find the point where all of this computational stuff ends. There's a lot of it. Okay, so let's just talk about interpreting correlations. So there are a couple, criteria or a couple standards in terms of interpreting correlation. So when we calculated our correlation by hand using the roundabout formula, we ended up with a 0.83. But what exactly does that mean? As a general rule, and these guidelines are geared a little bit more towards let's say the social psych realm, but anything from 0 to 0.1 or a 0.2 we would say is really no relationship. There's really nothing going on there. A 0.1 to a 0.3 or a 0.2 to a 0.4, depending on who you're asking, we would say is a weak relationship, but there's something there. It's just not that strong. 0.3 to a 0.5 or a 0.4 to a 0.6 is considered a moderate relationship, so pretty decent, not bad relationship in terms of its strength. And a 0.5 to a 1 or a 0.6 to a 1 is considered to be a strong relationship. So like I said, these conventions are probably not what Pearson would recommend. These tend to be just more, again, when you deal with social psych research, you kind of deal with lower effect sizes. So this is generally how we interpret some stuff, but you could basically bump all these up to be the official ways to interpret correlations. So again, something up to 0.2, 0 to 0.2, you'd be like, really nothing going on. 0.2 to 0.4 would be a weak relationship, but something there. 0.4 to 0.6 could be a moderate relationship. Pretty substantial, not so bad. And then 0.6 to 1, we would consider that to be pretty strong relationship there. So most research produces correlation coefficients in the neighborhood of 0.3 to 0.5. So typically speaking, when we're doing correlational research or doing these stats, we're ending up with moderate effect size, essentially, right? Moderate strength correlations there. Remember that you don't see any negatives in here because we deal with absolute values when it comes to the strength of correlation. The negative sign doesn't tell us anything about the strength. It only tells us about the directionality of a correlation. So remember, positive correlations, as one variable is increasing, the other variable is increasing. With negative correlations, as one variable is increasing, the other variable is decreasing. So when you want to know about the strength of the correlation, just look at the number, just look at the actual coefficient, and ignore the sign. Take the sign into consideration, of course, when you want to know the directionality of your correlation. So how can we interpret correlations? Just by kind of looking at them. Again, this is my guesstimates. That's why these are not equal signs here. These are about this, right? So taking a look at this first scatter plot. Not bad, right? There's a clear shape going on. I guesstimated that to be about a 0.5 or so. There are actually little like games that you can Google in terms of guessing correlations, and they're kind of fun, good for practice. They'll give you a bunch of scatter plots that look like this, and you have to basically guess what the R value of these scatter plots is. So let's go down here. When we take a look, I guesstimated this to be about a 0.7. Yeah, maybe it's more 0.6 or so now that I'm looking at it. Or maybe 0.65, somewhere in between, maybe. But clearly, we see the directionality is negative. So let's keep it as about a negative 0.7 here. It's a much tighter distribution of scores or pattern of scores than the first one, but there's still quite a bit of space, quite a bit of variance between these scores. Going up here to the upper right, you see these scores are getting really tight, right? Kind of getting really close to. They really want to kind of fit on a single line there. So they're not all lined up perfectly. We don't have a perfect correlation here. But I had guesstimated that as being around aboutish a 0.9 in terms of strength. And of course, when it comes to directionality, we see that as we are increasing with X, we're decreasing in Y. So we're dealing with the pretty strong negative correlation. And then finally, this bottom scatter diagram of scores. It looks kind of all over the place, right? Looks like there might be like just a hint of some type of relationship going on, but it's really not defined much, right? And if we look at it, it kind of looks like there might be a really small kind of like positive relationship going on, but it's definitely not impressive, not convincing. I guess they made that as about a 0.2 or so. So the point of this was to just kind of give you an idea of what these these numbers that we're producing, right? These coefficients, what they actually mean. Like, what does a 0.9 mean? Well, it means that's a pretty damn strong relationship you got going on between those two variables there, right? And throw in the negative sign. We know the directionality as well. And when we talk about a correlation of say 0.2 or so, you could be like, oh, kind of like barely maybe something there. 0.5, 0.7, pretty strong, pretty good, not bad, right? 0.5 we say kind of moderate. So I would recommend, if you got some downtime, bored, go Google guessing correlations. There's a bunch of programs out there that kind of act like they're kind of like games that you can play to try to guess the strength of different correlations. It'll help you kind of like visualize and understand what these coefficients, what these R-scores actually mean. Okay, so when it comes to correlation and causality, hopefully this is something that has been drilled into your minds in 221 and basically every psych class that reviews methods a little bit at the beginning of this semester, is that correlation does not equal causation, right? So it's important to keep this in mind, that just because two variables are related does not mean that one is causing the other one. There's a couple of reasons why this is possible. The first is that it is possible that the x variable is causing the y variable. That's certainly not outside the realm of possibility. But it could also be that the y variable is causing the x variable. There's kind of arbitrary what we labeled x and what we labeled y. So we have a directionality issue. Which one's causing which? We don't know. We also have known as the third variable problem. It's not even just the third very problem. It could be the infinite very problem. But this is to simplify things, is where third variable, let's say z, a variable z, is causing both x and y. Some other variable that we didn't measure or didn't even think about, and there could be dozens of these, or hundreds of these, or thousands of these variables that we don't know. Right? We can't measure all of them. And then, of course, we might have just found this relationship due to pure coincidence, just by chance alone, right? We could calculate a p-value and find out whether our results are statistically significant or not. But yeah, until we can rule out coincidence, that's always a possibility. So we never want to make causal claims just because two variables are related. When it comes to, let's say, that there's a strong positive relationship between having anxiety and depression. That's a true example. If you have one, you typically have the other. They tend to go hand in hand. One possibility is that having anxiety is really kind of depressing, right? Constantly worrying, constantly having these physical symptoms that come with anxiety can kind of wear you down. Another possibility is that being depressed is causing anxiety. Having these feelings and having these sad thoughts and morbid thoughts might actually cause anxiety in people. So who knows which is causing which? Another possibility is that maybe it's an imbalance of neurotransmitters in the brain, some other variable that's actually causing both anxiety and depression. So there could be a number of these. This is one example of a third variable, but like I said, there could be how many, who knows how many other variables that are actually causing both of them. And then of course there's the always the possibility of coincidence. An example that I just threw in here is that I'll read it because I know I'm blocking off my head or face or whatever is blocking off some of this. But since the 1950s, the atmospheric CO2 level and the crime levels have increased sharply. It would be a fallacy to claim that atmospheric CO2 levels causes crime, or that crime causes an increase in atmospheric CO2 levels. It's just a coincidence, right, that both of these things are happening. It doesn't mean anything. They're not related. It's just coincidence. One thing that we should talk about before I open up SPSS and just show you how to run a correlation in SPSS is this notion of the coefficient of determination. Now, when it comes to the coefficient of determination, it allows us to calculate the proportion of variance in one variable that can be accounted for by the other variable. So what exactly does that mean? This is not the easiest concept to grasp at first. Believe it or not, it's not the easiest concept to teach, because we can't use the word cause in here. So we have to use words like accounted for or explained by to try to kind of explain what we're getting at here. But to calculate the coefficient of determination, you just take your correlation coefficient and you square it. So in our last example, or the data that we've been using of exam scores, the number of hours students studied and what they got on their exam, we found a correlation of 0.83. If we were to square that, so we take 0.83 times it by 0.83, we would end up with a coefficient of determination, or R squared, of 0.69. So 0.69, remember, that's a proportion. And how do we change proportions into percentages? Well, let's get rid of that decimal point and slap on a percentage sign. So we can think of this 0.69 as 69%, right? So how we can think about the coefficient that we got, the correlation that we got, this 0.83, if we squared it, we can actually find out how much of that exam score can be explained by the number of hours that students studied. And in this case, because I made up a bunch of, it was just fake data, right? But in our case, it's 69%. That means 69% of the differences in exam scores that we saw can be attributed to the number of hours that students had studied, or the differences in the number of hours that students studied. So that means that the number of hours that students study is accounting for, it's explaining a lot of the differences we're seeing in exam scores. Not all of it, right? But a lot. There's still 31% missing here. So what's that what makes up what's explaining the other 31%? I don't know. Who knows, right? We didn't look at any other variables. We only looked at number of hours studied, and the how much students are studying is making up or accounting for about 69% of those exam scores. Everything else, maybe the number of hours students slept before the test day, or their stress level or their anxiety level, all of these other variables, they might account for the rest of the 31% of it that goes into an exam score. But let's just say you got a 100 on the exam. I would say, well, 69% of that 100 I can explain by, or can be accounted for by how many hours that you studied. And then I would have to say, I don't know what the other 31% is, where that comes from. But in this case, at least we're able to know how much one variable can explain the differences of another variable. That actually helps us in terms of making predictions. When we get to linear regression, we're going to see R squared pop up a lot. And just remember exactly what it's saying. It's saying that this variable explains that much of this other variable. In our case, the number of hours that you study explains about 69% of what you're going to get on that exam. A bunch of other stuff explains the rest of it, but this variable explains 69%. So, like I said, the remaining 31% of the variability in the exam scores can be explained by variables that we didn't examine. Right? It's impossible to examine them all. That's for sure. So when it comes to coefficient of the coefficient of determination, R squared can also be used to compare correlations directly, but we will worry about that for some other time. I want to now just take a moment to open up SPSS and run our correlation and see if it actually matches up. Let me just go up to our calculations. So this slide here shows us with the correlation of 0.83, right? So this is what we got when we calculated our correlation by hand. Let's see what happens when we get SPSS. We open up SPSS, and again, I'm hoping that most of you have had some experience with SPSS. If you haven't, I posted a whole bunch of tutorials and startup guides on Blackboard, and we will hopefully, probably by the time you're actually viewing this, we would have had a synchronous class where we were actually going through SPSS and starting up SPSS, going through the basics together in real time. But really quickly, when you open up SPSS, it looks like pretty much any other database, kind of like Excel, except that we have two options down here. Data view, so this is where we'll be entering in our data, but variable view also. This is where we're going to build our database. Now, I want to try to create something that replicates this diagram here without all those z-scores. Hold on to this here. We got 0.83, right? 0.828 to be precise. But let's just go to the initial data set. Okay, so this is our initial scores. Let me enter those into SPSS, kind of just as they are. So I'll go to variable view, and my first, it's going to ask me here, what's my first variable name? The code name that you give it, I'm just going to call it hours. See, you're kind of limited in terms of how many characters you can use in that field. But under label here, I'll put in the full name of the variable. So hours studied. Okay. We only have 2 variables, so I'll just go to the next line, and this is exam grade. Just for the name of the variable, I'll put in grade, but in the label, I'll put in the full one, exam grade. Now it's going to ask how many decimal points that we want to enter or we want displayed. We don't have any decimals here, and it's not a problem. The default is to go 2 places with the decimals, but I legit got some ADD, and those things just distract me. If we don't need decimals, I don't need to see a bunch of zeros all across the screen, so I just get rid of them. You keep them in there for all for all I care, or all that the computer cares. It doesn't really matter, right? So okay, database is set up. We just entered two variables and named them. We're ready to enter in our data. So we see hours studied for our participant number 1. They studied 2 hours and they got a 70 on the exam. Participant 2, they studied 5 hours and they got a 90 on the exam. Participant 3 studied 3 hours. They got a 75 on the exam. Participant 4 studied just 1 hour. They got a 65. Not good, right? Participant 5 studied 6 hours. They got a 95. And our final participant studied 4 hours and they got a 65 on the exam. So I got my data. It's all entered. It's all ready to go. Right? So how do we run this correlation coefficient? How do we run this Pearson product moment correlation in SPSS? Well, pretty much everything that you're going to need in terms of analyzing data is going to be underneath this Analyze tab that hopefully you can now see. I think it was being cut off. But in SPS statistics, we see file, edit, view, data, transform. It's going to go to Analyze. Basically everything, like I said, that we're going to need for analyzing data in this course will be underneath this drop menu. So we're going to go down to correlate, since we're going to be doing a correlation, and we're going to choose bivariate. So bivariate correlation means, we'll just think of bi, that means 2, right? Variate, variables. So we go to correlation, bivariate. We choose bivariate because we're taking a look at the correlation between 2 variables. We'll click on this and we'll get this dialog box that's asking us which variables do you want to look at? Which variables do you want to compute this coefficient for? Well, we only have 2, so that's easy enough. We just select our first one, move it over to our variables. We'll select our exam grade, move that over to our variables as well. Now, remember, these are continuous variables. These are interval scales. Actually, it could be ratio scales. You could study 0 hours, and that really means you studied not at all. And you could score a 0 on an exam. So a 0 is really a 0. So we're dealing with ratio scales here. But interval and ratio scales are treated the same way. When it comes to correlation coefficients, hang with Pearson, right? Because these are continuous variables. When it comes to tests of significance, always to be safe, we go with a two-tailed test. It's just a more conservative test. Let's say a more respectable type of test in some circles than others. And we can go ahead and click OK. Let's just see if there's anything interesting under options. I don't think there's going to be. Well, you can get your means and standard deviations here for each of those. So we might as well. It's always good to have descriptive statistics to know what our means and standard deviations were. You can even get your cross products if you wanted to. So all those calculations that we did, they'll do them here for you. But we don't really need them. Means and standard deviations are good though. So let's get those and let's run this thing. See what we find. So when it comes to the outputs of in SPSS, when it comes to correlations, they're going to give you a matrix, and there's a lot of redundancy that exists in them. But let's first take a look. We see that our descriptive statistics for the number of hours studied, I remember off the top of my head, it was 3.5, and our standard deviation of 1.87. So we're spot on. Matches our hand calculations. The same with our exam grades. Now, if you remember, when we calculated Pearson particle moment correlation by hand, we ended up with an R value of 0.828, right? So that was the correlation that existed between the number of hours that students studied and the score that they got on their exam. And we could go down to this correlation matrix here. And one of the cool things, if you take a look right here for this little asterisk, is it's saying, hey, any correlations that are statistically significant, we flag those with an asterisk. So keep an eye out for those, right? So that's definitely good to know. But we could take a look at the number of hours studied, the Pearson correlation with itself is a perfect correlation, right? So this is the thing that's kind of silly in terms of the redundancy that exists in these correlation matrices. It's calculating the correlation between X and X. That's going to be a perfect correlation because it's the same damn variable, right? But what about the correlation between the number of hours studied and exam grade? We go over here and lo and behold, it's 0.828. Exactly how it was when we calculated it by hand. And it has a little asterisk next to it, so we know it's statistically significant. But there's also another way that we can tell if it's statistically significant. In SPSS, this sig is your p-value. So sig stands for significance, and the numbers that it gives you here is your p-value. So we're going to revisit this when we when I show you how to run t-tests in SPSS, the different types of t-tests in SPSS. But we already know it's statistically significant because the computer flagged it for us. But we also know that our p-value, because sig represents our p-value, p is less than 0.05. Our alpha value is 0.05. So long as our p-value is less than that, we know that we're statistically significant. So just again to show you the redundancy, SPSS will run it this way, comparing x to y, and then it's going to run it the opposite direction, comparing y to x. So it's the same exact information, except on the second row here, we have the exam grade, the correlation between exam grade and hours studied. It's the same value, 0.828, right? And it, of course, will calculate the correlation between exam grade and exam grade, and that's a perfect correlation as well. So just keep in mind when you're evaluating these correlation matrices in SPSS, it's going to be a lot of redundancy in there. Just keep your eye on the prize. We want to know what the correlation between x and y is. X, number of hours studied, y, exam grade. Boom, there it is. Okay, so hopefully this just kind of helped review or refresh, bring some of that good 221 information to the surface of your brain, because we're basically going to build off of these principles when we discuss linear regression, which is coming up soon, or next maybe. But in the meantime, take care, and I'll see you soon.